Okay, let me start our discussion over the power plant engineering, power engineering, out of which we are going through the steam generator chapter. Screen. Last days, the last day we have discussed the we have discussed the the circulation inside the boiler itself. So, where we have gone through a term known as circulation ratio or CR. Used this condition, it was defined as flow rate of the saturated water in downcomers and flow rate of the steam released from the drum itself. You know, as per our design, the drum is being supplied. The drum is connected to a downcomer at the below, at the bottom of it, and through the drum, through the downcomer, the liquid water goes down and goes down, enter into the riser, and in the riser, which is placed inside the furnace itself, is the riser is a portion, a major portion of it is converted into the fuel air, vapor and water converted into vapor, and it comes out from the top of the riser and goes to the drum again in the form of a mixture of vapor and water itself. And from the top of the drum, boiler drum, the vapor portion is being supplied to the heat superheater itself for further heating the matter. And we know that we have a circulation ratio. What is the flow rate of the circulation saturated water down to the downcomer? And what is the flow rate of steam released from the drum itself? So how much liquid water is coming down, that is what's going out from the drum, and how much mixture steam is going out of the drum from the for the supervisor. Both the cases we are calculating the ratio of the fluid coming out of the drum itself. One is water, one is vapor. And the circulation ratio is the flow rate of circulated water down in downcomer and flow rate of divided by flow rate of steam released from the drum itself. This refers to the amount of saturated water to be circulated through the downcomer riser circuit per kg of steam released from the drum. Means we want to know how much vapor come liquid saturated water, which is saturated with vapor, how much it is circulating throughout this downcomer riser circuit concern. Therefore, the CR, the circulation ratio M, which is the flow rate of saturated water in downcomer divided by mg, which is the flow rate of the steam released from the drum itself. So the total flow rate of the saturated water goes to mg plus m1 divided by mg plus m1 divided by mg, where mg is the steam plus mg is the flow rate mass of the flow of steam itself, and m1 is the flow rate of saturated water in downcomer itself. Now it can be write down as 1 by divided by mg divided by m1 plus m0 equal to 1 by tdf, where m, the mass of the circulated water flowing through the downcomer itself, m1, and downcomer riser circuit during the certain time. So we are having three terms: m, mass of the saturated flowing through the downcomer and riser through the downcomer riser circuit during the certain time, divided by the mass of the gas coming out of the drum itself. And the mass of the this mass m is equal to the mass of the gas going out plus mass of the water remains as fluid itself. So 1 by mg divided by 1 plus mv is equal to 1 by tdf, where mass of the liquid, and where tdf is the top dryness fraction here, where tdf stands for top dryness fraction. That is the quality of the liquid vapor mixture discharged from the riser to the drum. The quality of liquid vapor mixture discharged from the riser to the drum. So what is the amount of, it is a fraction, what top dryness fraction. Top means it is going to the top, it is coming back to the side of the drum itself. It is the quality of liquid vapor mixture. What is the ratio of liquid vapor air mixture inside the when it is discharged from through the riser to the drum itself. Now, these downcomers are fewer in number and bigger in diameter. What is supposed to be seen? If the downcomers are bigger and number of them is comparatively bigger for the same amount of volume of supply of water, the risers is supposed to be more in number and smaller in diameter. This is the test opposite. Riser should be number is small and drum wise it is diameter wise it is bigger. And downcomers are meant to make the water fully fall by gravity. Downcomer is supposed uh, not to supply by pump itself because it is supposed to be fall by the gravity itself. The in uh, bigger in diameter, less bigger bigger in diameter, less the pressure drop due to fraction. There's the pressure drop due to friction, since pressure drop is inversely proportional to the diameter itself. So what is going on? The higher for diameter, water falls by gravity. Bigger diameter will be less pressure drop due to friction, since pressure drop is inversely proportional to the diameter itself. We are having the formula delta of F into F into L divided by D rho into V square by 2, where F is the fraction, L is the length of the downcomer, D is the diameter, rho is the mass of ball, and V is the velocity square by 2. So the downcomers are made bigger in diameter, which may vary from 150 to 200 millimeter, even higher. Now MF, mass of the fluid, is equal to N pi d square into Pi into V, where Mi, mass flow of saturated vapor, where Mi, mass flow rate of saturated water in the downcomer. Saturated water, such pipe is saturated, it is fully saturated, or with either it is fully saturated with steam or totally water itself. To a certain extent, it is fully saturated with steam itself. Now, the mass flow rate in the downcomer is the Mi, and N is the number of tubes, D is the diameter of the downcomer, downcomer, and M is the PM and Pi, density of the saturated water at the boiler drum pressure. Pi is the intensity of the density of saturated water at the boiler drum pressure, and kg plus meter cube, and V is the average velocity of water in downcomers itself. So both the V's are average velocity of downcomer. That is the pressure differential, and and this is the Mi is the mass flow rate of saturated water in the downcomer itself. Just 1 second. Downcomer. Let us go through boiler supervision, control. Add pressure, temperature. In the diameter is 150 meter higher. MF, it is not Mi. MF is the mass flow rate of saturated water in the downcomer, and D and PF. PF is the density of the saturated water. And so the downcomers are now bigger. MF delta P, and let this delta we tell here V square by 2. V square by 2. Just 1 second here. Mm. Now, now here MF is the end pi by MF is the actually this is where MF is the mass flow rate, not MI, but MI mass flow rate of saturated water in the downcomer, N number of tubes, D diameter, PF is the density of the steel, PF is the density of the saturated liquid, saturated fluid, PF density of the saturated water at the boiler drum, and V is the velocity of the water itself. So we have getting get the for the flow, get the pressure difference in terms of got the pressure difference. If L, if what is F is the coefficient of friction. L is the length of the diameter, where F is the coefficient of friction, L is the length of the downcomer, D is the diameter of the downcomer, rho is the volume of the density of the saturated water inside the downcomer itself, and V is the rate of flow of fluid in the downcomer itself. So pressure differential is found in terms of coefficient of friction, in terms of length, D, rho, and V. And the diameters are made bigger in downcomers are made with bigger diameter, which are vary from say around 15 centimeter to 20 centimeter even higher. Then we got the mass MF, mass flow rate of saturated water, MF and D, V and water, all in terms of, so we got pressure difference as well as the density of the velocity and the average velocity of the water is downcomer. Now, the circulation velocity depends on the circulation ratio in the tube and may vary from 0.4 to 1.5 meter per second, 1.5 meter per second, depending on the capacity. Thus, the number of downcomers required can be estimated from above equation. So circulation velocity is the, what is circulation velocity? It depends on the circulation ratio, may vary from 0.4 to 1.5 depending on the capacity. Thus, so many numbers of downcomer required can be estimated from the above equation. It can be 6 or 8 or as high as 20, again depending on the capacity of the steam generator itself. Let us go for the next one. Now, what is the function of the riser? Riser absorbs the heat from the furnace itself. And for the same total cross-section area, the smaller the diameter, larger the surface area exposed to the hot gas for heat transfer. So smaller the diameter is the less, means the volume of the surface area of the exposure of the charger is less. But for the smaller the here, they due to heat transfer got to hot gas for heat transfer itself. The risers are of small diameter. The smaller the diameter, the larger the surface area. Smaller the diameter and larger the surface area exposed to the gas, hot gas for heat transfer itself. Therefore, the risers are of smaller diameter. Means the more number of diameter risers should have less diameter and more number, so that the larger cross-section surface area is exposed in terms of larger number of the riser itself, and it goes through the hot gases, through the hot chamber, and through the hot gases for where heat is being transferred from that gas to the water itself. Risers of smaller meters, around 60, say around 62.5, around 6 to 7 millimeter, and larger in chamber, larger as compared to and comparatively larger in diameter compared to the larger in number compared to the downcomer itself. Now, it is required that the nucleate boiling should occur in each riser tube. Nucleate, it is required that nucleate boiling should occur each riser tube, and film boiling is supposed to be avoided. Nucleate boiling, and what is the nucleate boiling? What is film boiling? You see, what is that? Nucleated film boiling and film structure and the nucleate boiling. Now, we have too much steaming and less circulation ratio. Too much steaming and less circulation ratio. Uh, Too much steaming and less circulation ratio uh, in a riser may cause a departure from the nucleate boiling (DNB) and an offset of film boiling. And an onset of film boiling means the gases are formed in a film and not in a nucleate form, like your bubbles which has come out in the vapor gases. Vapors are supposed to form in terms of bubble and not in forms of film itself, which may cover the inside surface of the riser itself. Now, if it's steaming out is too much and circulation ratio is less, means less is the circulation ratio, means too much steam is going out, and comparatively less amount of water is coming inside the through the downcomer to the riser. There may be an formation of film outside the riser type itself. The water tube should be high heat absorbing area of the furnace, and you see internal twister and springs which break the vapor films and retard the onset of DNB, as figured in early page, as shown in the figure in the early pages. What is DNB? Recently, the water tubes are in high heat absorbing areas of which area of the furnace of which it is furnace are provided with internal tube twisters. Now, what is happening here? It should have the nucleate boiling should occur in each riser tube, and film boiling is supposed to be avoided. And too much steaming and less amount of circulation ratio in a riser may cause a departure from nucleate boiling and an onset of film boiling. Means what is film boiling? What is nucleate boiling? That is some nucleate or droplets of boiled water or steam should come out with the boiling water itself, and this is the preferable. And if uh, a film of moist is created, which is outside the sun, outside the surface of the tube itself, then it creates problem, because water in the water tubes inside the furnace is a very high heat absorbing areas of the furnace, and provided internal twisted and springs which breaks the temperature films and retard the onset. And for DNB, where and as in the figure in the furnace. Recently, the boiler tubes in high heat absorbing areas of the furnace are provided with internal moist twisters and springs, which breaks the vapor film and retard the onset of the DNB, and the to be uh, to be ripped helically on the moisture on the to be ripped helically on the inside surface are often used now. This ribbing creates a centrifugal action that directs the water droplets in the upper film and clinging to the surface, and so much so and wash it away. So what is going on? That what is told here is how the saturated water comes from the downcomer should boil inside the riser itself. There should We should prefer nucleate boiling, and should occur film vapor over each riser tube, as the film boiling is supposed to be avoided. So boiling should be done like this. There will be volume or droplets or nucleates comes out from the water itself. Nucleates of vapor comes out from the water itself, and should not be a film of vapor, which should create we may form a layer to the surface of the tubes, causing the less amount of heat transfer. And if your steaming process, if the absorption of steaming is too much, then the circulation ratio may cause a departure from sealing to DN nuclear from the departure from nuclear boiling DNB, and an outset of direct nuclear boiling, and outset of film being outset of film boiling. Recently, what will happen? All the water tubes are high heat absorbing areas, and provided boiler tubes are provided with internal twisters, some bent, some springs, which breaks the vapor film inside the vapor film and make the nuclear is formed, and retard the onset of declared the onset of direct nuclear boiling as shown in the figures. Recently, the water tubes with high interface area in the furnace are generally provided with internal twisters and springs which breaks the vast internal twisters, some bent, some uh, springs should be given which breaks the vapor film and retard the onset of the DNB, means nuclear boiling itself. The to be briefed helically on the moisture inside surface are often being used now. This reeving creates a centrifugal action that directs the water drop less than the rest to the moisture film and clinging to the surface and easy wash it away. Now, the void fraction alpha of a two-phase mixture, often called volumetric quantity, often called as volumetric quantity, is defined as the volume of vapor divided by volume of liquid by volume of vapor. Totally, total volume of vapor is liquid and divided by the volume of liquid plus volume of the vapor. The amount of water and amount of vapor, and the numerator amount of vapor. This alpha is the volume fraction of a vapor in a liquid vapor mixture, volume fraction of vapor in a liquid vapor mixture. The quantity X is the mass fraction of the vapor in the two-phase mixture, volume fraction and mass fraction. First, alpha is the volume fraction of the mixture and X is the mass fraction of the mixture. While the specific volume of a mixture of X of quantity S, which is the mass fraction, is given by V into 1 minus X into Vf plus X into Vg. Means X is the brightness fraction, where X is the mass fraction of the vapor. If you multiply with the specific volume, volume per unit mass, will get the mass of the vapor, and 1 minus X is the difference. It is the fraction of the water in the water multiplied by the Vf is the uh, Vf is the specific volume of the fluid itself. So Vf is equal to, thus Vf is equal to X into Vfg. This density of the mixture of voltage of mixture of volume alpha is given by this density of the mixture of voidage alpha, mixture of voidage, this is voltage. Alpha is given by V into 1 minus X into Vf plus X into Vg, V plus X into Vg. The density of the mixture of voidage, alpha is given by 1 minus alpha into rho into I, rho into F plus alpha into alpha into Pj is equal to P into rho into I plus alpha into Pij. The volume of gas and air multiplied by the fraction of mass fraction of vapor, and it should be added with 1 minus alpha into Pi. It's 21. Let us come Consider a two-phase flow in a riser itself. Two-phase flow means riser contains liquid and saturated liquid water and vapor mixed with it. Let AG is the cross-section area offered by the saturated liquid. AF, that is not G, but AF is the cross-section area AF is the cross-section area occupied by vapor bubbles, right? AF is the cross-section occupied by the saturated liquid, and AG is the cross-section area occupied by the vapor bubbles. What is this AG? AF is the cross-section area occupied by the saturated liquid itself in the riser, and AG cross-section occupied by the vapor bubbles only. Means what is the cross-section occurred by the water which is saturated with fluid, that is AF, that is AF means fluid, AG is the gas, cross-section area of the vapor itself, of the bubble which is occupied by itself. So the dryness fraction of the mass is cross-section area of the area offered by the vapor bubbles divided by AF plus AG, and 1 minus alpha is equal to AF minus AG plus AF. Thus, it becomes AF divided by AG is equal to 1 minus alpha divided by alpha, 1 minus alpha by alpha. Now, when a two-phase mixture is moving, the vapor, because of its buoyancy, has a tendency to slip past the liquid itself. That is, to move in a higher velocity than a liquid. The shift ratio S is defined as two-phase mixture is moving. Okay, one is water and one is vapor. The vapor, due to its buoyancy, has a tendency to slip past the liquid. Means it will move further than the liquid water and move at a higher velocity than the liquid water. So the slip ratio S, this is called the slip here. The slip ratio is the velocity of the vapor divided by velocity of the liquid itself. That is Vg divided by vapor divided by Vg of the fluid itself. At any cross-section of the area, it is greater than supposed to be greater than the unity. Means the velocity of vapor always will be better than the velocity of the liquid itself. Now this quantity x is given by mass of the gas divided by total mass. The mass of the gas divided by total mass itself. So rho into G, velocity of the gas, cross-section area occupied by the gas, and a specific volume, and the velocity of fluid, velocity of the gas, velocity of the gas itself, velocity of the vapor itself, divided by m into Vg. Thus, the equation becomes As into Vg m Vg, and thus Vg becomes m. Vg is a vector m1 minus m to the m into Vf, m divided by m into Vf divided by Af. So from equation 3 and 4, Vg by Vf is equal to x. From these two equations, we get the Vg of equation Vg and Vf is equal to x Vg Af divided by Ag into 1 minus s squared itself. So the S, the slip which has been measured by the experimentally and found vary between 1 to 10. Slip ratio has been measured every experimentally and found to be vary between 1 to 10. Approximately 1 at high pressure, where the liquid and vapor denies approach to each other, and slip ratio has been measured experimentally, this slip ratio, and to vary and to vary between 1 to 0, 1 to 10, approximate 1 at high pressure where liquid or vapor denies approaching to each other. As the pressure increases, the slip ratio decreases. From the equation 5, by rearranging, we'll get alpha is equal to 1 minus Vg into x into divided by x into Vg in plus 1 minus x into Vf and Vf into S. So if we simplify it further by dividing both top and bottom by x into divided by Vg, that is the velocity of the gas itself. So it will become 1 minus Vg it becomes 1 plus 1 minus x divided by x into Vf by Vg into Vf by divided by Vg multiplied by S itself. Now alpha thus becomes 1 by 1 plus 1 minus alpha by alpha into 1 by 1 divided by tau, where tau is the df by dg. Tau is subsequently calculated by df by dg. So similarly, x is equal to 1 minus 1 plus 1 plus alpha divided by 1 minus tau psi. This axial fluid gives selective verification of the high flux variation. The axial heat flux distribution to the riser can be used to determine the political reactions. The maximum density distributed rho is now found from rho is equal to 1 minus alpha multiplied by rho f, means density of the saturated water, and density of the vapor plus alpha into density of G. Now the average mixture density in the riser is now obtained from rho m 1 by h 0 to h into rho into z to dz, where z is the axial distance from bottom of the riser, is the axial distance from the bottom of the riser. In the case of uniform axial hearing, the above equation has been to yield rho m equal to rho I minus rho g divided by 1 minus I, and putting all the value here, 1 minus psi xr 1 minus 3 1 minus psi, where alpha c is the void fraction of the richest riser circuit. Then the total pressure head produced due to density difference is found from equation delta P G into H rho into dm, and is balanced by the pressure losses in the loop itself. Thus AP G into H rho into M rho minus PM plus rho into PD plus PX rho into PD plus PX and delta PD plus delta X and delta G and delta P heater. where delta P0 where delta H0 stands for pressure loss in downcomers by Pascals, PR pressure loss in the riser due to Pascal, and pressure in the bent, pressure due to loss in pipe pipe, pressure due to pressure loss into the heater. All are in terms of Pascals. Provided there is no conversion of pressure to kinetic energy as the fluid is discharged from the riser into the drum itself. So we are not converting the vapor pressure into the kinetic energy or moving something. It is just discharged from the riser to the drum itself. Now let us go to the steam drum. We have one downcomer, we have one riser, and we have one big drum which is defined as a steam drum. What risers do? They discharge into the drum a mixture of water, steam, and foam and slag. So risers is doing supplying steam water, all right. At the same time, certain slags and certain foam also. Steam must be separated from the drum before it leaves the drum. So from this mixture, you have to get the steam, not the other items. So any moisture carried with steam to the superheater tubes contain dissolved on the salts. As in the thus in the superheater, water evaporates and thus where slags, salts remain deposited on the inside surface of the superheater and to form slowly forming a scale, which is difficult to remove itself. This scale reduces the rate of heat absorption and ultimately leading to failure of the superheater tubes by overheating and rupture. The superheater tubes are exposed to the highest steam temperature and pressure and temperature on the inside and maximum gas temperature on the outside. So they are made with costliest material. So most care is taken to avoid so that no drainage of done to it by the excessive convener carryover of moisture with the steam. So superfast superheater is extremely made with extremely costly tubes, and you should say you don't have to here is exports. Here is the structure of working. What happens? The evaporator tubes, highest steam pressure and temperature on the inside, they got it, and the highest temperature on the outside due to flue gases. They are made with costliest material, and still they are supplying costliest material, so that almost care is to be taken so that no damage is done to it by the excessive carryover of moisture with the steam. Some of the impurities of steam is vaporized silicate. Impurities of steam is vaporized silicate, which may be caused with turbine blade depositors itself. Next comes okay. Nobody's arrived. I am stopping this lecture here.